Today's video lesson is dealing with the kinetic formula in a first-order reaction. What I have in front of me is my equation page that was handed to you the day we got our note pack out. What I'm examining from our formula page is the first-order reaction in which A is converted to B. We understand from the past few lessons about what's known as the differential rate law, staring down those data tables of initial rates and generating how the rate and concentration are related. In a first-order rate law, rate is equal to K times the concentration of our A raised to the first power. And since A is a reactant, we also express what's known as a rate expression, where the change in concentration of A over the change in time is known as the rate expression. Recall that as time goes by, the concentration is disappearing for the concentration of A, our reactant. In the new lesson presented today, we are going to take the differential rate law and turn it into what's known as an integrated rate law. Through the help of calculus, we are turning our curve into a straight line that has a y equal mx plus b format. By changing the concentration on the y-axis and the time on the x-axis into a straight line function, we are now able to relate the concentration of the reactant at any point in time in our experiment. Recall that in a differential rate law, we always begin with instantaneous rates. We're assuming that no product has formed. By integrating the rate law, and again, the math understanding isn't important, but to understand that by taking the curve and creating a y equal mx plus b format, the natural log of the concentration of our reactant A at any point in time in the reaction can be found by taking negative K, that's the rate law constant, times the amount of time that went by, plus the natural log of the original concentration of A. If we were to graph, y on the x-axis is the natural log of A. That's equal to negative K, where negative K is the slope of the line. This rate constant is the slope of this line. Since it's in a negative format, you see the negative in front of it. The x, of course, is the x-axis represented by time, usually in a second. And then, of course, the intercept here would be the natural log of A at time 0. This is where we're heading in the new lesson, is taking smaller steps to look at how a differential rate law can be used when integrated to calculate the amount of reactant left in solution at any point in time during the course of a reaction. I'm going to keep my kinetics formula page close by. We'll be referring to it again, but I'm going to ask that you find your note packs and we'll follow along. We're on page 6 where it's reading about the concentration with time. Friends, this is also available on the website in a PowerPoint format. The PowerPoint is on a different link. If you'd like to look at that as well, feel free to do so. I'm going to choose to just look at the note pack, what we have in front of us. We are studying section 4, the change of concentration with the change in time. We are looking to take our differential rate law and integrate it, what we discussed a moment ago. In our first bullet under this section, it reads, rate laws enable us to calculate the rate. Let's go ahead and fill in the rate from the rate constant and reactant concentrations. Rate laws, just as in the example up above, rate is equal to K times the concentration of each reactant raised to some power. We are going to take a look at how the constant and the concentration can be used to calculate rate. Rate laws can be converted into equations that tell us the concentrations of the reactant or product in any point in time during the course of the reaction. To understand the calculus will be Mrs. Milder's job. We will share with you the formulas to go from a differential to an integrated rate law, taking a curve and turning it into a straight line formula. Now, in a differential first order rate law, it describes exactly how the rate depends upon the concentration of each reactant. differential rate laws of what we've been practicing. Rate is equal to K times the concentration of the reactant raised to some order. We are seeing today that an integrated rate law describes how the concentration out of a reactant at any point in time can be calculated. So we're looking at how all the differential rate laws, there is an integrated rate law and vice versa. For every addition problem, there is a subtraction problem. For every differential rate law, there is an integrated rate law. Remembering that rate laws help us understand in our last sections how reaction mechanisms work as well. Rate laws give us great insight into the number of collisions necessary to produce a desired product. So remember, differential rate laws show us the relationship, such as rate is equal to the concentration of our reactant A changing over time, and we've expressed that as rate is equal to K times the concentration of A raised to some order. Could be first order, second order, our most common ones that we're solving. Differential rate laws, in the next bullet says, shows how rate depends on concentration of reactants. I stare down data tables looking at rate and how it's influenced by manipulating each reactant, holding others constant. The concentration of the products do not appear in the rate law because it is an initial or instantaneous rate. Remember, at time 0, there are no products. They haven't been made yet. We also remember from our previous lessons that rate laws have nothing to do with stoichiometry, but must be determined experimentally. They can't be obtained from the equation, but they must be derived by looking at data. Moving from what we know already and have practiced, differential, to the new lesson today, integrated rate laws. It reads, if we integrate this equation, this relationship can be transformed into an equation that's related to the concentration of A at the start of the reaction to the initial concentration at time 0. And that is going to give us another time called T. Any other time that's gone by, we can calculate the remaining amount. For those of you who are familiar with calculus, that relationship would be set up. Concentration of A at any point in time and compared to time 0. You might have seen this in Mrs. Milder's calculus class, but this is all we're doing. We set that familiar equation to integrate, and what we're able to do then is to compare the remaining amount of reactant A over a course of time, knowing reactants get used along the way as products get made. Again, this part, not important, but just showing those who are interested. We'll move to our second page on this particular lesson. When we begin looking at concentrations as a function of time, we refer to those as an integrated rate law. So let's fill that blank in. The concentrations as a function of time, and what that's allowing us to consider, not only can we figure out the initial amount of our reactant, we can figure out how much reactant is left over a course of time simply by knowing the rate constant K, which is the slope of our line. So it forms an equation that depends on the order of the rate law, differential. If rate is equal to the change in concentration over the change in time for our reactant A for any power, that power that we deal with is known as an order. We could have a 0 order, a first order, or a second order. Those are the ones that we will focus on. Now remember, on our equation page, we have a first order area, a second order, and a 0 order. I threw on the calculus form for those who are interested, but again, not critical to us for chemistry. Math is just a tool. Don't tell Mrs. Milder. When I set that aside, remember we'll focus on first order and then we'll move to second and so forth. So let's begin looking at our kind of having our equation page set aside, we'll look at what's known as a first order integrated rate law. And we'll begin by considering this equation. Suppose we have 2 units of N2O5 producing 4 units of NO2 and an oxygen. If we found that the rate is equal to K times the concentration of N2O5 in its first order with respect to our reactant. As soon as I see that first order, I now know where to focus my attention on my equation page. It's first order with respect to our reactant. And I also noticed that it had nothing to do with the stoichiometry involved with that reactant N2O5. If it's first order, we understand that the concentration doubles, the rate doubles. If the concentration were to triple, the rate would triple, and so forth. If we integrate this equation with respect to time, we get what's known as the integrated rate law. We do not need to memorize these. The equation sheet is there for your convenience. When we integrate, we get the form where ln stands for the natural log of our reactant, N2O5, at any point in time of our reaction. The natural log of the concentration of N2O5 at a point in time is equal to negative K, the rate constant, at that point in time, T stands for time, plus the natural log of the concentration of N2O5 at time 0, the initial amount provided to us. ln is a natural log key on our calculator. It is very different than log, so make sure that we're finding ln when we hit our formula. Negative, this is a dash, it's not a negative sign. The concentration of N2O5 at time 0 is given to us in data table format as the initial concentration. Our differential rate form, just to review, rate is equal to K times the concentration of A raised to the first power. However, the integrated rate form for a first order, the natural log of whatever our reactant is at any point in time, can be calculated by knowing negative KT plus the natural log of the original concentration amount. This is the general form you will see appear on your equation page. Notice that it is giving us a y equal mx plus b format, which is a straight line graph. So if we were to consider graphing this particular line, it gives us all kinds of information. I know that the x-axis represents time, usually in a second. The y-axis would be the natural log of A. I have a negative slope. That's why the negative sign appears to flip it to be positive for K. So the slope of the line is negative, the value of K. K constants are never negative. So the negative slope is flipping that to be positive if we were asked to solve for that. So if we're looking at that straight line, we could prove it's straight order or first order reaction by simply using our calculator to graph natural log of A set over a certain amount of time. We could certainly prove to ourselves that we get a negative slope that would fall into a straight line. Some people will express this reaction in terms of a ratio. The natural log and the ratio would consider the original amount of concentration over that reactant over a course of time equal KT. I don't tend to use this equation, I just wanted to show it to you. I find the one that's more useful is the straight line, y equal mx plus b format. Here's a practice. Let's take a look at our first practice. It reads, the decomposition of a certain insecticide in water follows first order kinetics. I underline that so it just brings my mind to the part of our equation sheet, first order. It gives me a rate constant of 1.45 per years. What that tells me is the value of K. It makes sense that if it's first order, the concentration unit doesn't appear. 1 minus 1 is 0. For first order, it doesn't show up. And the temperature is 12 degrees Celsius. A quantity of this insecticide is washed into a lake on June 1st, leading to the concentration of 5 times 10 to the negative 7 grams per cubic centimeter. Assume the average temperature of the lake is 12 degrees. They're mentioning that, so we're assured that the temperature remains constant and does not play a role in the kinetics. Constants, the K values, are temperature dependent, concentration independent. So we want to make sure the temperature does not influence the rate. So it's just sharing with us it did not. Question asks, what's the concentration of the insecticide on June 1st of the following year? 1 year has gone by. How much of the insecticide is left? We know it's a first order kinetics problem, so the formula we pull out from our formula sheet, it's asking us about the remaining concentration over a course of time for 1 year. The natural log of our insecticide, I'll call A, after 1 year, is negative KT plus the natural log of the original concentration of the insecticide. Let's place in what we know into the formula, seeing that the target is the concentration of A 1 year later. The natural log of A 1 year later could be found by taking negative rate constant 1.45 per years. T in our equation stands for the time that went by. That's 1 year. Notice how I'm making darn sure that my K constant time matches the time unit I place into the equation. The K was given in a per year. I wouldn't want to put 365 days for the time. I match the unit. Plus the natural log of the original concentration, 5.0 times 10 to the negative 7th grams per cubic centimeter. What we should do is simplify the right-hand side. When I simplify the right-hand side, I'm going to need a little room down here, so I'm going to leave this space available for the next question, but I'll continue this problem down here. I'm just out of room. When I simplify this, I leave the natural log of A, what I'm trying to solve for, equal, and let's hit our calculator. Negative 1.45 times 1 plus, parenthesis, the natural log, and that automatically places a parenthesis on my screen, 5.0 e negative 7, close my parenthesis again, so there's 2 on it. I find my calculator saying right now it's negative 15.96. That's simply kind of just number crunching what I have on the right hand side. The natural log of A 1 year later, the concentration remaining at 1 year, has now been simplified to be this value, negative 15.96. We want to pull out A. We don't want a natural log associated with it. Now if you look on top of your ln key, natural log, you see an e raised to the x. That's known as Euler's number, e. We're going to have to hit that. We want to know e to the negative 15.96 is going to give us the concentration of A 1 year later. So on my calculator right now, I have negative 15.9586 still on the screen from before. I'm going to hit second function, ln, and now I see on my screen e raised to the caret and negative 15.96, close my parenthesis, and I find a value, 1.17 times 10 to the negative 7th. The concentration unit from up above was grams per cubic centimeter. After 1 year that's gone by, that's the remaining amount of our insecticide. We started with 5 times 10 to the negative 7th, and now a whole year later, there's 1.17 times 10 to the negative 7 grams per cc remaining. Now along with this question, How long will it take for the concentration of the insecticide? How long will it take? Looks like we're being asked to solve for t. That's the time variable. How long will it take for the concentration of the insecticide to drop to 3 times 10 to the negative 7th? We know the initial concentration from the story problem. It started at 5. It's dropping down to 3. How long is that going to take? So what we'll need to do is set the natural log of 3 times 10 to the negative 7th grams per cc equal to negative K constant, 1.45 per years to the negative 1. We'd like to know T. Now I ran out of room there, so I'm just going to carry that down where it says plus the natural log of the original concentration, 5.0 times 10 to the negative 7th grams per cubic centimeter. Our target variable, right there, the time that went by. Simplifying, I would start simply by hitting the natural log of 3e negative 7 minus the natural log of 5e negative 7. When I hit equal, I'm at 2.67. Now I'll divide by negative 1.45. And I get T equals 0.352 years as my answer for T. We'll continue with another try in first order kinetics. Top of page 8 in our notes reads, the decomposition of dimethyl ether, which has a formula CH3 taken twice O at 510 Celsius, is a first order process. It also tells us the rate constant, 6.8 times 10 to the negative 4th per second. I did not mean to superscript the time. That was an error. So let's see what we have. First order tells us, turn your attention to the first order kinetics right here. The rate constant is given as 6.8 times 10 to the negative 4th. That should be superscript. This should be seconds to the negative 1. Since it's a gaseous reaction, it's going to talk about pressure given in torr. Instead of molarity units, we will now use torr for pressure. So our first order reaction would look like the natural log, and we use the partial pressure of our reactant, CH3 taken twice to O at any point in time. P, of course, is partial pressure. I'm just putting parentheses around that, is negative KT plus the natural log of the partial pressure of our reactant, CH3 taken twice O, and I'll close the parenthesis and put a 0 to say the original amount of pressure. No difference in the math, I'm just showing partial pressure instead of big M molarity units. If the initial pressure is 135 torr, that's this guy at the end. What's the partial pressure after 1420 seconds? I check to see if my rate constant matches the time unit. It does indeed. It's in a per second. The natural log of our reactant, I'll just switch to A at any time t, is equal to negative K given to us, 6.8 times 10 to the negative 4th per seconds, times the amount of time that went by, 1420 seconds, plus the natural log of the original pressure given to us is 135 torr. We want to know the partial pressure of our reactant after 1420 seconds have gone by. When I simplify by hitting the right-hand side, let's do that together on our calculator. Negative 6.8, second function e negative 4, times 1420 equals, right now I'm at negative 0.9656 plus, parenthesis, natural log of 135, close parenthesis, twice. Right now, I have a value of the right-hand side simplified as 3.94. We want to know the partial pressure of our reactant without the natural log in front of it. So that's our E raised to the 3.94. So on our calculator, partial pressure of A, I hit second function, ln. Now my screen is saying E caret key. And I'll press in 3.94, close parenthesis, and my answer, 51.4 torr. Oftentimes we talk half-life. Half-life is particularly important when we think about radioactive decay. How much time does it take for the original amount of reactant to reach half of that amount? So the time required to reach half of the original concentration, I'll write that as the original concentration at time 0. That's what we're measuring with a half-life, the time required to go half as much. In the first order reaction, just to share, this is on our screen here as well. The half-life for first order reaction is the natural log of 2 over K. And just to share that development is a little bit of math here. When the concentration of A equals the original amount divided in half, when time is exactly 1/2. That's what we're looking for. And simplifying that integrated rate law, the natural log of 2 set equal to K times the half-life. So what we're looking at really is just simplifying the natural log of 2. Test it on your calculator. If you hit natural log of 2, it reads 0.693147. I sometimes think it's easier to memorize natural log of 2 instead of 0.693, but whatever you find to be most easiest. The half-life in a first order reaction is the natural log of 2 set over K, where K is the rate constant given to us typically in the formula. So the time to reach half the original concentration does not depend on the starting concentration. It will in second order reactions, but it does not for first order. In other words, the natural log of 2 is equal to K times our half-life, half the time that went by. This is often an easy way to solve for K, the rate constant. If you know the half-life, you can solve for K. If you know K, you can solve for the half-life simply by looking at that relationship where the half-life is equal to the natural log of 2 over K, which is the same as 0.693 over K. Whatever you find easiest, perhaps you like either one. So a first order half-life does not depend on the starting concentration. And it remains constant throughout the entire reaction. It will be different for a second order reaction. So the concentration of the reactant decreases by 1/2 in each of a series of regularly spaced time intervals, namely T1/2. Radioactive decay is a prime example in a nuclear reaction. The more stable an isotope, the longer its half-life. The quicker the half-life, the more unstable that radioactive decay. So let's do a little practice here. Practice with the half-life reads, the decomposition of N2O5 into 2 units of NO2 and half O2 in a carbon tetrachloride solvent is first order with a rate constant of 6.2 times 10 to the negative 4th per minute at any given temperature. What is its half-life? Half-life is equal to the natural log of 2 set over K. We are solving for the half-life given the K constant. So the natural log of 2 simply set over 6.2 times 10 to the negative 4th per minute. And if we hit that on our calculator, natural log of 2 divided by 6.2 E negative 4 My calculator is reading, and it's pausing for effect. I didn't hit it right. Hang on. Sorry, gang. Natural log of 2 equals divided by 6.2 e negative 4. Now I have it. 1117.97 minutes. Down at the bottom, what is the time required for 20% of N2O5 to decompose? 20% is not half, so I would not use the half-life formula. That's only convenient if it's indeed exactly 1/2. But I can use my first order, where the natural log of our reactant at any given time is negative kT plus the natural log of the original amount. So we want the time. T becomes our target variable. If 20% has decomposed, let's plug in what we know. The K constant, so I'm looking at equals negative 6.2 times 10 to the negative 4th per minute. So that's the K. T, that's what we're trying to solve for, plus the natural log of the original value. And that original value, if we read back up here again, let's just say 1. And we're picking an easy enough number because remember, first order, and it just really is a critical point, does not depend on the starting concentration. If we pick a concentration of 1 and 20% of it has decomposed, what's left, 20% of 1, is 0.8. We could pick any numbers, but I think those two are quite easy. So if I have an original value of 1 and 20% of it has decayed, I have 0.8 left over. Let's simplify this, pulling out for time. Again, I would hit the natural log of 0.8 equals minus the natural log of 1 divided by negative 6.2 e negative 4, close parenthesis, time here, 359.9 minutes. Minutes matches the unit on the K value. Let's pause. We're now at the top of page 9 in our note pack. We're going to now consider a second order. A second order brings us to this particular section on our equation guide. If A is going to be in a differential rate law, we would recognize that as rate is equal to K, where K is our rate constant. The reactant A now raised to the power of 2. If I integrate that, we turn it into a straight line formula. Differentiation and integration are opposite. It's finding a straight line curve in a y equal mx plus b format. We end up with the following formula. Again, the calculus not important, but seeing how now the concentration of our reactant can be calculated after any period of time has gone by. This time we end up with reciprocals. The original concentration set under 1, the concentration remaining after a certain amount of time set under a 1, and notice now the slope has become positive. Positive slope indicates a second order reaction. We still end up with a y equal mx plus b formula, where y, the y-axis, is 1 over the concentration of A. Time is the x-axis. The m is the slope of our line represented by K. And again, the interception, the b, the y-intercept, would be the original value of A reciprocal. So let's take a look at how that develops. Our differential rate law we just explored shows rate is equal to K times the original concentration here. Second order shows that that exponent is a 2. When we integrate that rate law, we show 1 over the concentration of A after a certain amount of time has gone by. This shows me how much concentration of A is left after time went by, set equal to K, the rate constant, and T is that time that went by in our formula, plus 1 over the concentration of the original amount, times 0. We get our formula, y equals mx plus b, where y, 1 over A, and this is after a certain amount of time. K is the slope, T is the x-axis, and the y-inner slope is the original concentration of A set under a 1. Here's the big clue. If we plot a series of data and we get a straight line where 1 over the concentration of A versus time shows a positive graph, we know it's second order. However, just to keep in mind, if we get a slope that's negative, where the natural log of A over time shows a better straight line, that's how we can determine a first order reaction. We'll be entering lists into our calculator to see which one gives us the straight line. If it's a negative slope, first order, positive slope, second order, checking out that correlation coefficient on your calculator screen, the R constant, seeing which one gives us a closer number 1. So, important, one way to distinguish between first order and second order is to graph both, graphing a natural log of A versus time, or graphing a reciprocal of A versus time and comparing them. We just said if first order shows natural log of concentration versus time is linear, or a second order reaction would show the reciprocal of A versus time, gives us a better straight line. Let's begin a little calculator skill in the following lists. We'll need our graphing calculator out. Let's turn it on. Hit the stat key to go to your lists. I need to clear mine, so I need to clear list 1, list 2. And now they are. Let's enter into list 1 the time values. We'll hit 0, enter, 50, enter, 100, enter, 200, enter, and 300, enter. I'll bring the cursor over to list 2 and plot the following. 0.01, enter. 0.00787, enter. 0.00649, enter. 0.00481, 0.00380. I now have list 1, list 2 entered into my calculator. I'm going to use the calculator to generate a list 3, which I'm going to use to represent the natural log of the concentration. I'm going to make the calculator do the work for me. So what I'm going to do is to place my screen, my cursor, on list 3, up on the very top where it says list 3 up here. Now it's ready for me to hit the formula. So now that it's highlighted, I'm going to hit natural log button, and notice on the bottom it's giving me ln with a parenthesis, and I want it to find the natural log of those concentrations. So I'm going to hit natural log of list 2 equals. And now in list 3 we see a generated set of numbers that automatically calculated those natural logs. It reads negative 4.605, negative 4.845, negative 5.037, negative 5.337, negative 5.573. We also need to consider a list 4. In list 4, what I want in there, I want the reciprocal of list 2. So I want the concentration of our reactant, NO2 or A. It looks like I have flipped. That's really NO2. But let's make the calculator do that for us. So again, I'm going to move my cursor to the top of list 4. That allows me to type in a little calculation. That calculation will show that I want the reciprocal, so 1 divided by, and my concentrations are still in list 2, so I hit list 2. 1 over list 2 generates the concentration of that reactant in a reciprocal, it reads 100, 127, 154, 208, 263. We need to find the best straight line, a y equal mx plus b. Is it what we're looking for if the x-axis in list 1 is time, list 3 is the natural log of our concentration, and then again we want list 1 time, list 4 is our reciprocal of our concentration. We need to plot those in a graph and find the best straight line. So stat, calc, a linear regression, which is number 4 choice. It's asking me which list would you like? Well, list 1, comma, list 3 is going to show me the ratio between the natural log and time. And this is what my calculator says. I get an A value, a B value, R squared, and R. I want to know the correlation coefficient. So under here, I'm going to jot down R squared is 0.9824. Friends, you could take the time to visually plot this. I'm just using the correlation coefficient to save myself from plotting. The closer this value is to 1, the better the choice would be. If you do choose to graph, and just hit the graph key to show that graph, it's going to end up showing you what the graph ends up to kind of come up a little bit like this. Whoops, I'm not showing it on the screen. So what we're looking at, where the natural log of A set over time is giving me a negative slope, but it's showing a curve. Let's try again a linear regression, but we'll use the second set of data, time versus the reciprocal. So stat, calc, linear regression is choice 4. I want to do list 1, comma, list 4, and see what information I have. The R squared is 0.99998, so forth. You can see the R squared, best I can, I'm trying to show that, 0.9999. When I graph this, if you choose to show that to yourself by actually visualizing the graph, you get a straight line. 1 over the reciprocal of A set over time gives me a straight line. I simply choose to look at the R constant. If it's close enough, I might have to choose to graph for visual effect, but I rely on the calculator to do the hard work for me and save myself from graphing. This is definitely showing a better correlation to a second order reaction. This set of data shows a straight line with list 1 in time, list 4 is reciprocal. Therefore, we know that the best choice is first order. Excuse me, second order. I circled the wrong answer. Second order. So, couple of interesting things. Y equals mx plus b, where of course the slope of the line is the rate constant. You can pull that right from your screen as well, where mx plus b, and you can find what we call A for m. There's the K constant right on the calculator screen. You can see it here. So the K constant can be found at the same time you're graphing. Now I'm used to saying y equal mx plus b. This calculator is ax plus b, but that's the slope of the line. So this value from the calculator is giving us the K, the rate constant. Practice this. Consider again the decomposition of NO2. The reaction is second order with respect to NO2. The K constant is 0.543. Notice that's exactly what was on our calculator screen a moment ago for that, the slope of the line, the K constant, 0.543. So again, that's verified in the next part of our problem to match the second order choice. If it's second order, the molarity to the -1, second to the -1 makes sense for that rate constant, doesn't it? 1 minus the overall. If the initial concentration of NO2 is 0.05 molar, what is the remaining concentration after 0.5 hours? there's a little trick here. 0.5 hours, half an hour, but the rate constant is in a per second. So consider that as we're getting ready. 0.5 hours matching into the per second. Here's what I know. There's 60 minutes in an hour, and there's 60 seconds in every 1 minute. So I'm converting half an hour into the number of seconds when I do that. 0.5 times 60 times 60 is showing me, not that, excuse me, try again. 0.5 times 60 times 60, I get 1800 seconds. So the reason I did that, when I plug into my formula for second order rate law, I want the rate constant time to match the time that I place in the formula. Second order says the rate of the concentration of a reactant over a certain time interval is kT plus the reciprocal of the original concentration. It's plug and chug. Let's see what we find. Here's what we know. The rate constant, 0.543 molarity and seconds to the -1. The initial concentration in a closed vessel was 0.05 molar. The time we determined to be 1800 seconds. How much of that is left after 1800 seconds went by? I think I'll choose to start with the right-hand side and simplify. 0.543 times 1800 equals plus parenthesis 1 divided by 0.05. 1 over the original concentration, or excuse me, the concentration remaining after these 1800 seconds went by. I'm seeing on my screen 997.4. We want to pull this out. So the algebra would show that these two values just simply switch numbers. We're going to multiply both sides by that concentration of A and then divide both here. So just to rearrange this, I'm sure that the algebra would be friendly. What we end up doing is 1 divided by 997.4 equals that concentration of A at that remaining time, A representing that NO2, the decomposition reactant. Going back to this part, we're trying to solve here, knowing this value, in your head just flip those. That's what the algebra will show. 1 divided by the answer still on my screen. 1 divided by 997.4 gives me an answer of 0.001 molar, the remaining concentration after 1800 seconds. Check to see if it makes sense. The original concentration 0.05, this value is smaller. That makes sense. Reactants get used. A lot of time went by, so you got used up a lot. Let's pause. The next section I'd like to consider is a practice with second order half-life. I'm not real fond of the way that I ended up having this typed, so I'm going to just cross this off in my notepad and just refer us to the way that I kind of have it better written on our formula page. The half-life for a second order reaction, and that's what T half means, is 1 over the K constant times the original concentration. Notice that I'm noticing here that the original concentration does play a role in second order half-life. It did not play an order up here with first order half-life. It was just simply knowing the K constant could get us there. So a little bit different formula. I like to see that as T1 half equals 1 over K times the original concentration. And what that means to me, and just kind of a side note, the lower the concentration of that original value, the greater the half-life. It takes longer to decompose. In contrast to behavior of first order reactions, the half-life for second order and other reactions depend on reactant concentrations. and therefore it changes as the reaction proceeds. It's going to slow down. So therefore, it's a different value each time, whereas in the first order, it was a constant. In a zero order rate law, zero order, we understand that changing the concentration does not change the overall rate. That brings our attention to this area on our formula page, zero order, where A goes to B, but A has absolutely no effect. So look what happens. Rate is equal to K times the concentration of A raised to the 0 power. That's going to drop out. Rate is the rate constant. And what we notice then when we begin to integrate this rate law to get a straight line axis, it's simply a direct comparison to the concentration of A over time. No natural log, no reciprocal, but a direct correlation. K will end up to have a negative slope, so we put the negative in front of K to make sure we report K as a positive value. Our y equal mx plus b form says the concentration of A remaining at any point in time is equal to negative KT, that same point in time that went by, plus the original concentration. And we also can see on our formula page the half-life for a zero order, the original concentration set over 2 times the rate constant K, 1/2 the concentration that was original over the constant K. So we're just really looking at those formulas. So a zero order, the rate does not change with concentration. The integrated form says the concentration of A is directly equal to negative KT plus the concentration of A original value. And when A is exactly half the original value, we call that half-life. Just the definition of half-life. How long does it take for the original value to be exactly half gone? And what we saw there, and again from the formula page, no need to memorize, that the concentration of A original value set over 2, that's 1/2, that's a half-life, times K, the constant. These are not common. Zero order half-lives are not commonly calculated. Our text does mention them, so I will as well. A little bit of surface area chemistry when we're talking about enzyme chemistry or metal-based catalysis, it may play a role there. But again, not often appearing in an AP type problem.